Okay, so we're doing lab 14 today. We're skipping 13.
Okay.
Okay, you're way ahead of me. And
The link for the homework, lab 14, goes to lab 14. But if you put in the right URL, it's fine.
okay, I'll get that fixed. Thanks. Anyway, wait for a few more people to get here and then go ahead, and you can go kind of slow on this one.
Okay.
Okay, fix the link. Sure enough.
The girl wasn't even like.
Okay, we got 16. I think we can go ahead and start. So, is everyone able to see my screen share and also hear me?
I can hear
Okay.
you fine. So, yep, you got some yeses.
What we're going to be looking at today is data models and graphing. So what the heck does that mean? Well, we're getting into the part of the course where it becomes evident how important visualization is. It's all well and good when we can do whatever methods we want to on the data we get, store it in whatever we want. But for most people, if we can't visualize it in some way, it's going to be very hard to talk about it. So that's what we're going to deal with today. Let's look at the data we've got here. It's going to be a simple y versus x kind of data. We've got a fraction of the methanol mole, and we have in the liquid phase, and we have the same measurement in the vapor phase. So we're taking some, what would you call it? Well, it's methanol in one form of matter, which is liquid, and either through change of temperature or pressure, we're going to turn it into a vapor. And with the change occurring from liquid to vapor, we're going to measure the fraction of methanol in the solution. Okay. So doesn't really matter what the particulars of this data is for our purposes. All we know is we have an input and an output, and we can plot these in a visual way. So how do we normally do that? Well, if we were doing it by hand, we would have something kind of looks like this, and then for each one of these points, like 1 1, we'd have something over here, 0 0, we'd have something over here, and then we'd measure each one and maybe get it somewhere wherever it was, and then we'd have the ability to, if we want to, put a line through it so that we can see kind of what's going on as the x changes, the independent variable changes. Well, we can do that with code also. Here we have a black box, just like I mentioned to you on one of the previous homeworks. It might actually be the same one. What does it do? Well, it lets us plot stuff visually. It's going to use all of the matplotlib stuff from one of the packages for Python, and it's going to take as an argument the following. We've got a list of our x values, y values. If we want, we have an additional list of x and y. Then we've got the label for x, label for y, and we've got the title. Okay, now that we have that, maybe sometimes we can use it. We're going to make a couple other functions. It's going to make our lives easier. We've got one called linear. This is a linear data model where B0 and B1 are simply the y-intercept and the coefficient in front of a x. Surely you have all seen something like this in algebra. And similarly, we've got a quadratic model, which instead of y equals something x, we've got up to x squared. And we've got something for x to some power. And here, well, I'll explain this one when we get to it. Now let's actually use some of that stuff in an example. So this is the values we had before. So 1.0, 0.882, 0.765 seems to be the same data. Now, what are we going to do? Well, we are going to plot this, and our goal is to try and get a line that might go through the points, kind of like I mentioned before. So let's do that. What it's going to do is ask us for some, I'm intentionally putting in things that would not be a good one. The red points here are our data. So 1.0, 1.0, that would be here. And you get 0, 0, which is here. And what we want is the blue line to go through as many of the red points as we can get. We want a line of best fit. So that's the game we are going to play. Is given different inputs to our linear model, we're going to try and get it to look better. So question 1, what is a linear model? I've actually already gone over it. So if you're paying attention, it should be pretty easy. So I entered -5 here. What does that mean? What's this? What's the blue line? How does that correlate to my -5 at all? How would it change if I put -4, -4? The slope is -5. Yes, it is. What else is -5? Yes, the y-intercept is also -5. So if that's the case, what might, I have some kind of function, right? Where we're just going back to algebra, like y equals x plus x squared or something like that. So if I've got b0 and b1, what does my function look like? Y equals something. What is our y equals formula for a linear model? Yes, there it is. Y equals b0 plus b1 times x. That was right here. Okay, so if that's the case, what we're really wanting to do is get the formula we make with b0 and b1 to go through as many of these points as possible, or something like that. So let's try 0, 0. That just means that y is equal to 0, always. And we get a straight line that looks like this. But this lets you see what the red points kind of look like better. So let's play the game of trying to get a good line. Now, what is a good line? That's a very good question. We're not in the business of answering that right now. We're just trying to get a good one. You kind of know it when you see it. So someone give me a value for b naught. Q. Oh, okay, 1. All right. Someone else give me a value for b1. 2, 3. Let's try 2. We had 2 votes for 2. All right. So here's the result we get. And what I'm actually going to do is I'm going to put this twice so we can see the change in what we're getting. So earlier I did 0, 0. And that got us this. And 1, 2 got us this. I'm not really satisfied with either of these. But what this does tell us is that when I change the intercept from 0 to 1, it went up, to here. And then the slope went way up like that. All right, so we know how it's changing. So let's try again. What should my y-intercept be? What should b0 be? 5. Interesting. So we went from 0 to 2, and that moved it up. And we're going to set it to 5, and it's going to move it way up. Okay. What should our slope be? b1. And there's nothing wrong with just putting in random stuff so you can start seeing the pattern. 1. Okay. That gives us what looks like a better slope. The old one kind of looked like this. And that is, if we were to try to shift these down, we had the old one that looked like that, and the new one kind of looks like that. So the y-intercept is just too high. Maybe we can stick with the slope we have and choose a different intercept. So someone says, let's try b0 equals 0 and b1 equals 1. Okay, 0 and 1. Okay, that's pretty good, I think. It's better than what we had. It at least hits 2 points completely, and it's closer to these. So here's the question. Is this a good fit? Are we satisfied? No, it needs to split the data. Okay. It still misses most points. Okay. Well, what if I were to tell you this? If you were to get the line that actually hits the most points, it would still not be, you could still do better. So what if what you guys are starting to say is maybe we shift it up a little bit. Let's try 0.1 and 1. All right, so that shifted it up, maybe a little too much, but it looks a little closer. So here's the point where I'll ask, what do we mean by closer? How do we measure and say that one line is closer to what we want than another? Other than saying I'm just looking at it and it looks closer. How can I relate the blue line to the red points? Well, think about it this way. When I actually hit a point, what is the difference between the red point and the blue line? Zero. So if I were to hit every point somehow, what would be the total number of differences? Yes, it'd be zero. And that's the perfect line, right? Is a perfect line the one that hits all of the points perfectly? Or can we do better? Can we do better than that line I was talking about, the one that doesn't miss? No, correct. The line that perfectly hits every single observation is as good as you can get. Unfortunately, these points are not on a line, so we can't get to perfect. However, we now have a way of saying what the perfect line looks like. And what is that? It's the smallest number of differences. So if I take the difference between here and here, the blue and the red, add it to the difference between the here, blue and the red, do that for every point, add them all up, then I have a measure of differences. That is what's called the residues. Now, what I'm going to do is I'm going to run this one because I think this is the one that's in, well, I suppose it doesn't matter. This is the one we just ran, I believe. So if I print up the residues, I get this value here. And we want this to be as small as possible. So if I run this one, I get 0, 1, run the residues again. I could copy this twice, but so it appears that this one here, 0.1 and 1, is a little better. In fact, I'm going to copy this twice just so we can do this properly. Okay, so we got 0, 1 and 0.1 and 1, and we want the residue number to be smaller. Is anybody confused on what the residue number is? Because that is super important. If you don't get that, then the entire rest of that's the main point. Because it doesn't make any sense to do any of these methods unless you know what they're trying to minimize. What they're trying to do is get to the perfect line. And sometimes you can't have the perfect line. So how do we get as close to the perfect line as we can? We try to minimize the residuals. I would please, I'll beg anyone who it doesn't get it to ask. Okay, so let's see, what's the last one we ran? It's this one here. So let's try 0.5. Wait, no, not 0.5, 0.05 and 1. That gets us there. Calculate our residues. And I'll run this one 0.1 and 1. And what is our residual? 0.02, 0.03. Okay, so it still seems like this one's the best. Now, is anyone noticing a pattern of what we're doing here? I am plugging in numbers, calculating the residual, and then choosing the residual that has the smallest one as the better of the two. Can anyone tell me how long I'm going to do this? And I'll, if you can give me a humorous, sarcastic answer, I'll appreciate that too. But you can either give me the real answer, and I don't know, or something funny. Until I stop, that's pretty good. It's both funny and true. Because we've left out something very important here. And that is what I will call the tolerance. And what I mean by the tolerance is a problem like this is usually given as follows. I want you to find the line of best fit until the residuals go below 0.05. Once we finally get to a point where it's below 0.05, we can stop. Because, as you can tell, as actual zero is impossible because, and I'll change this to blue, the plots don't form a line. So I can't get perfect, which means I could do this forever, or at least until I run out of time. So I need to pick a point where I stop. And why is it important that I pick a point where I stop? Because the same thing happens to the computer. If I were to tell the computer, keep going until you get a perfect line, it'll just run forever until I stop it. So we need a point to say where we stop. And I think we're already pretty good. But regardless of the method you use, linear, quadratic, power, residue, anything. Actually, never mind. Any method you use. So what is the linear method? Well, I'm trying to fit a line. What is the, I've never used this one. What is the quadratic method? Well, I guess that works. I'm trying to fit some kind of curve. What's the power method? Well, I'm going to be using x to the something. It's going to look like that. I'm just trying to fit, let's call it a curve, because even a line is a straight curve. I'm trying to fit a curve to a plot. And eventually, I either have to stop or say that the perfect solution is obtainable. Okay, so let's try doing the same thing with a quadratic model. And just like before, I'm going to make two of these so that you can get a sense for what the machine would actually do. Because, well, here's an interesting question worth going into. Can anybody tell me, gotta make sure I get it correct. Can anybody tell me what the first computers were? Using the modern sense of the definition, I suppose. I'll even give you a hint. The question I posed it as, I said, what are, I use the word what, is dehumanizing. It used to be a job title, very correct. Humans used to do it. In fact, as the stories go, I can't remember her name, but she was the one in charge of a group of women because they were not on combat roles, just calculating away. Humans were the ones that did these tasks. So being able to describe these as we would do is the same methodology we use to describe it to the computer. So once we get this to the point to where you can say, oh, okay, I can see how I would do this. Now you're ready to tell the computer how to do it. That's why we're visualizing this. Okay, so let's try this with a quadratic model. We've got our same data, but now if you think back, what is our quadratic model? It looks like this. Y equals b naught. That is our intercept, plus b1 times x. That's our slope. Plus b2 times x squared, which is our curvature. You don't even have to really give them that title. B naught is the coefficient of no x. B1 is the coefficient of x. B2 is the coefficient of x squared. That's all you really need to know. All right, so let's start tinkering. What's a good one to start with? I'm going to need 3 numbers. So someone give me 3 numbers. And I advise you to start with simple stuff. -1. And I definitely don't advise you to start with, like, if you've already done it to try to make something fit, don't give me that as the first one, because that kind of ruins the exercise. So -1 as a b naught. Anybody got a, okay, 2? Anybody got a curvature? Uh, 0.5, I can do that. All right, here is what we've got as, now what the heck are we trying to fit here? Well, as we had before, we had a line. This time we don't have a line. We've got a curve we can try to fit. All right. So this one, well, problem one is it goes up and we want it to go down. We want the curvature to be negative. We know that. Now, well, let's get the residual. We calculate as 4.87. Okay. So well, before I do that, someone give me a tolerance that we can go with that we can try to fit. It's whatever you guys want. I'll let you guys pick. And don't pick something huge, like 10. Plus or minus 0.5. Okay, we can work with that. So with a tolerance of 0.5, I'll show you the one I would start with. I would start with x squared, just because it's easy to see what the data would look like. And this one may even be better, the one we started with. So 0 for B naught, 0 for that one, and 1 for that one. That's what I would start with. Okay. Which one's better? Well, it's hard to say visually, but now we can actually say here. So this one has a residual of 0.76. This one has a residual of 4.8. So why did I pick this one? Well, it's because this is y equals x squared. It's as I know what this looks like simply from having a lifetime in algebra. And it'll be easy for me to kind of mess with it from here. All right. So I think everyone can agree that x squared is the better one. So we don't need to change it. So we want to change this one. So going from x squared, what do I want to change? And I suggest we change one thing at a time. You can either change the intercept, change the slope, or change the curvature. So what do we want to change? Curvature, okay. So these will stay as 0. What do I want to change the curvature to? I put it in as 1 earlier. -1, okay. All right. So that puts it at going down here, and the residual is going to be quite large. But it's not the end of the world. If only I had a way that, you see how there's kind of a slope here? What if I could turn that slope up? What if I could make this go up somehow? Maybe there's a way to do that. Anybody have an idea? Well, let's see what happens when we change the values. I'll just try this one first. 1, 0, -1. That moved it straight up. That went like that. Okay. Well, let's go back to what we had. Curvature of -0.3. Okay, sure, we can do that. 0, 0, -0.3. Okay, it's less going down. And the residual's still too big, but it's better. What we haven't messed with is the B1. The B1 is the slope. So let's mess with that. So we have 0, 1, -0.3. Hey, that's kind of neat. What did it do? It took our curve. The curve didn't change, but its slope did. It went from kind of facing this way to facing this way. All right, or maybe we're onto something here. Let's calculate the residual. 0.42. That's better than this. Okay, now we've had a better one. So the one we've got is 0, 1, and -0.3. So what should we change? Do we need to change it up and down? Do we need to change the slope? Or do we need, so Reed says B1 equals 1.3. I'm getting good participation today. That makes me happy. So we'll leave that one alone. 1.3 and -0.3. Hey, that's pretty good. Did we reach our tolerance? Almost. Oh, I don't think I ran this yet, did I? We reached our tolerance. Very good. Okay, so you kind of get an idea for the method here. I highly encourage you start out with something very, very simple, which in our case was x squared, and then tinker with one thing at a time. We saw what happened when we changed the y-intercept. It moved it up and down. That didn't help. So we started changing the curvature. That did help. Then we started changing the slope, and that helped a lot. So now you know what to tinker with. Only change one thing at a time. Why would you want to change one thing at a time? Because it's called isolating a variable. And this is just a problem solving tip in general, not just for this class. If you've got something with multiple variables, if you change too many at once, you won't know what made things better or not. All right, let's try the next one. We're going to use the power law here, which is, I'll show you the formula. Y equals B0 plus B1x to the power of B2. Okay, so we're going to do the same thing. I'm going to copy this. Oh, wait, I think that's the quadratic. Yeah, it is. Copy this, make double, do that, and do that. All right. All right. So what's something easy to start with? We're doing something. So B0 plus B1x to the power of B2. I'll let you guys pick. What should B0 be? Zero. I agree. That's a good one. What should B1 be? I think 1 is reasonable. What is B2? 2? Yeah, that's fine. It's going to be literally one of the things we just saw, but that's fine. But now we can start messing with things. Which one should we mess with first? Well, question 1 is, what about our line? The blue line is not satisfactory. Do we need to move it up or down? No, so we shouldn't mess with B1 yet. Do we need to change the slope? Maybe. Do we need to change the inflection of the curve? I think very much yes, we do. Okay. Well, we're cheating a little bit because we already know something that kind of works, but that's fine. So what if we try now? We want to change only one thing at a time. We know that this needs to probably be something negative. So what should we give it? We'll use the same one, 0, 1, and something. -1, sure. Okay. Well, instead of using 0 as the, I'll try to explain what is going on here. So we have B0 plus B1 times x to some power. Instead of using -1, what we want to do is treat 1 as the line we go across instead of 0. So we can use like 0.5 or 0.3 or something like that. That was a little surprising for me too. All right, try 0.5. Good choice. 0, 1, 0.5. Hey, that's not bad. At least it doesn't look bad. Let's see what the residual is. And I'm going to nominate, we go for 0.01. That's what we'll go for, since this is the last part of the example. Okay, so we have our curvature flipped. It's not super bad. What should we change? We want to make B2 0.7. Okay, we'll try that. 0, 0.7, and 0.5. Okay. Let's check the residual. 0.3 versus 0.09. So that was a little bit much. Let's see if 0, 0.9, 0.5, if we even want to change it at all. 0.09, 0.06. Okay. So here's what that thing appears to do. When we change the B1, that was not a good start. It changes how much this comes down. No big surprise, because what it does is it changes the slope. No, it's not bad. It's a good. It was a good. That this process is full of guessing too far in one way. Someone says try keeping 0 and 1, but change B2 to 0.7. Okay, we can do that. So let's see which one was closer, 0.09 and 0.0. 6. So this is the closer one. So this is the one I'll change. All right, 0, 1, and 0.7. That looks pretty good to me. We have a residual of 0.05, and I said 0.01. I think I said that incorrectly. We have a residual of 0.005, and our tolerance was 0.01. So we've passed it, which means this is good enough. All right. So based on the fact that I put in numbers from you guys, you seem to grasp the process here. The process is start out with something basic and try tweaking one of the values to get to where you want to go. Let's see, exercise. Okay, now choose which data model to use and make the estimate. Okay. This is the quadratic. Please input. Okay, so let's try 0.25. Well, I thought it would let me do it. Oh, I see what happened. I used my number pad, and apparently, didn't know this would happen. I changed the cell from a code cell to a markdown cell, which is weird. Now I have to restart everything. Very cool. Stand by. Okay. All right. So what we have here is instead of plotting outright, what it's asking for, and I'll even move this down so that we can see it all on the same screen, is if I input a value, it's going to give me the output based on whatever estimation we used. So if we use the quadratic of 0, 0, 1.75, and negative 0.8, we get an output of 0.388. So I said, what's the value for 0.25? Which should be, so 1, 2, 3, 4, 2, 3, 4. It's pretty close. Let's see what happens if we use the best one we had. We did 0, 1, and 0.7, 0, 1, and 0.7, but we used the power. I want to make sure yeah, power law. Okay. 388 is what we had, and 379 is what we just got. So the power law approximation that you guys made was better than the one that was just in there to start with. Sam says a really good quadratic is 0, 1.5, and 0.5. Okay. 0.25. Oh, negative. I was about to say 0.25. Yeah, that's pretty good. Let's try 1.0. Yep, that's pretty good. All right, so you kind of get the point of what's going on here. If it's more difficult to see what's going on here, that's a very good reason why visualization is so important. We are individually plugging in 1 point at a time and getting the output. Okay. Let's look at example 2. We have the same data above. This time, we're going to use interpolating polynomials as in the lesson. So interpolate is a verb, and polynomial is a formula like this. So what does it mean to interpolate polynomial? Let's go from one to the next until you have the one you want. So that's what we're going to do. All right. We're going to build an interpolation function. Not terribly important, at least I don't think. Lagrangian interpolation is something I went through in scientific computing, not a freshman level course. So I would just say, trust me that this is a basic interpolation method that we know works very well. Okay, so this is our interpolation function. We've got our data. Here's the empty list to store what we're going to get. Step size, important, showing us, you know, how we went, hey, try changing this much, try changing this much. That's what this is. This is going to say how many times do we do it. And we're going to build our predictions here. And this is all for plotting. Okay. Hey, that's pretty nice. That's pretty nice. What are our residuals out of curiosity? My Zoom tab thing is in the way. This should, okay, not defined. Okay, we want Y table and this. Okay. This function was not built to use this data. I just copied it, meaning something in here needs to be plugged into something in here, and I just don't remember which one it is. Not terribly important. Okay. Let us, actually, you know what? Here's what I'm going to do. Rather than run through this one by one, I'm going to put that in a loop. And we're going to do it for all of them. So I'm going to say for x for I in x table. At least I think that's what it's called. Yep. We're going to say x table I. And I'm going to say for x equals and we had x table I. All right, so this should print out what we want. Oh, duh. Length. Okay, I'm derping something up, and that's okay because that's software engineering. Pal. Let's start with 1. We get 1.0. I'm going to bring these down so I know what to go through. 0.882. 0.882. And we get 9.29. 0.765. Get 849. Let's try one down here. 0.159. 241. So this is just a fancy way of saying that this is really good. What's the actual function? I'm curious. I don't know how to get it actually print out the coefficients, but what we've done here in a very short way of explaining, and I'm sure this is what the lesson was all about. This line here is inside of 2 for loops. What is it doing? It's doing the exact process that we were going through and saying, all right, try messing with this one, try messing with this one, try messing with this one. And it's doing it in terms of this step right here. So you've seen how to do it by hand, and you've seen a algorithm that I'm assuming is what you went over in the lecture. If not, I'm happy to answer questions about it. All right, let's take a quick look at the homework. Let's see, as far as grading goes, I spent most of my time grading the other section because I was behind. So after class, I'll be grading this section. I think, yeah, let's just leave it at that. All right. This is the normal, just we want your system info, not to sell to anybody, promise you won't, or I won't. Modeling by trial and error. This is going to be plot things in, use the following formula, create a list predicting your error, and compute the sum for your residuals. Actually, compute the sum of the squares. You've got your scaffolding for what you need to do. Your plotting, linear model, build the list of observation, build the list of the model, actually plot it, and get the sum of the squares. Do you guys know what I mean by sum of squares? I'm assuming that's what was in the lesson today. No. Okay. Here, it's pretty simple. Remember when I talked about residuals and what they really are? That's a good one to look at. Yeah, that's a good one. So I talked earlier about what the residuals are. It's this point, which is the one we want, minus the actual distance we got to. It's the absolute value, so it doesn't matter which one you take the difference of. You want the difference, one minus the other, take the absolute value. Okay. Add all these together, and you've got your residuals. But there is, and the reason this works better, I will just tell you that it does, and that it's the standard, rather than go into why explaining it, because I've only got 3 minutes. But rather than adding these together, here's what we do. We take all of these and square them, and then add them up. So it's nothing crazy. Rather than saying this plus this plus this, blah, 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 we say this squared plus this squared plus this squared plus this squared, blah, blah, blah. So that's what we mean by sum of the squares. Oh, and that's actually what we were doing. I just didn't notice. So this first number is the pure residuals. And this number, which is the one we were looking at, is the sum of the squares. Yep. So if you were clever enough and knew how to press a certain key combination that would take highlighted code and put it somewhere else, you might be able to make use of that. Okay. I will look at that in a second. Exercise 2, different model. Same kind of thing, but instead of y equals b naught plus b1, x, you've got what looks to be quadratic. Exercise 3, you've got what looks to be cubic. Exercise 4, you have an exponential. And exercise 5, this is a question which looks to be answerable in English. So give me something I can read and understand. If you just say yes, then I probably am not going to give you full credit. So use the one you chose to get some input and output for 12, 16, 21. Exercise 6. Let's see. This is the interpolation. So what I did in the lesson or the lab at the very last bit where we got as close as we did, do the same thing. Okay. On the homework, I get this error. Do you know why? X and Y must have same first dimension, but shapes. Yes, at least I'm guessing. I don't know which one you're working on, but if you were to try to plug in X values is like 1, 2, 3, and Y values is 1, 2, 3, 4, then these do not have the same dimension. This one is 1 by 3, one row. Yeah, 1 by 3, and this is 1 by 4, which won't work because now you have a Y value that has no input. Or if you did it vice versa, you've got an input that has no output. Okay, well, it looks like most people decided that the recording would suffice for the last couple minutes, but that's fine. It is 9:50. So any questions, comments, concerns, or something else? Don't see exercise 6? Don't know what to say about that. Did you try? Are you sure the thing you downloaded says exercise 14 at the top? Because when I started out this morning, the link wasn't okay. Well, if you don't see an exercise 6, oh, okay, he must have removed it, so that's fine. I will make a note of that. All right then. Everyone have a good day, and I will have office hours tomorrow at the usual time. Thank you.